resistance. This is one of the ones that we've looked at, and we've been dealing with this, and you would have dealt with this in year 2 when you did your practical. It's one of the dead tests, and it's quite a basic test. You know, it's one of the dead tests that we have to do. So the insulation resistance. Now, there are 2 main factors that affect insulation resistance: length and parallel circuits. So going back to our good old fashion, looking at our electrical science that we looked at, obviously when we increase the length of a copper cable or any conductor, obviously we increase the resistance, but we're also going to increase the possibility of leakage. So the insulation resistance of a length of cable is the resultant of a number of small individual leakage paths or resistances between the conductor and the cable insulation. These leakage paths are distributed along the cable. Hence, the longer the cable, the greater number of leakage paths and the lower the insulation resistance. This is because each resistance, although very high in value, is in parallel with others, as you'll remember from your electrical science. The more resistors connected in parallel, the lower the total resistance. So here you can see from this example, if we had a smaller area of cable, if I just get this little pointer working. So if we only had here, we've only potentially got 2 areas where we can leak between the cable conductor and the cable sheath. Obviously, the more this increases, the more potential paths we've got, the more parallel paths. So obviously the longer, which is, you know, the more chance that we've got. So, and parallel paths, also going back to electrical science, if 2 final circuits have a live and neutral insulation resistance, say of 100 mega ohms each, and an installation resistance is carried out on individual circuits, there will be 100 mega ohms for each circuit. So we're just testing one circuit here, doing the insulation resistance, and we're getting 100 mega ohms. If we do, like we're going to look at now, and you do a whole distribution board, and in this case, the distribution board might have 2 circuits, what we'll see is we get a parallel circuit. So if 2 final circuits, live and neutral installation resistance of 100 mega ohms each, and an installation resistance test is carried out when they are connected in parallel, the reading will be 50 mega ohms, because basically it's halved. So if we were looking back at our equations, we'd have 1 over 100 plus 1 over 100, which would give us 2 over 100. And then if we inverted that to give us our resistance value, we would get 100 divided by 2, which gives us 50. So the more parallel halves we have, obviously the lower the resistance. We're going to see a nice calculation now, which looks a bit daunting. So the more circuits connected to a consumer unit or a distribution board, the lower the resistance, the insulation resistance. So don't worry, it looks quite daunting, but we'll go through it step by step. So a small domestic installation has 6 circuits connected into the consumer unit as follows. So we have a cooker with 150 meg. We have a heater, 160. We have a ring of 180. We have another ring of 170. We have a lighting 140 mega ohms, and we have another lighting circuits of 120. Now, as you can see, all of those readings on their own are very good, very acceptable. What happens is, though, when we put them into this big equation, and we can use this onto our calculators and do the 1 over, and I know there's an example for you in the worksheet, so pay close attention. I'm actually helping you now. Do the 1 over, and you add them all together. With the calculation, we can choose the same denominator and things, but just by sticking them in a calculator, end up with this equation, which gives us the answer of 1 over our insulation. So we invert that, and it gives us a total resistance for the insulation for the whole circuits of 25.1 megaohms, which is really low. But that doesn't mean that one circuit is at fault. It's just that we're using all those in parallel. So if you were going to do a whole insulation of a whole domestic circuit or a consumer board, and you got a low reading, which wasn't acceptable or lower than you thought, then it would be test all the circuits individually, and then you find there wasn't really a problem. But it's just something to bear in mind, that because you've got all those resistances, if you added them up in parallel, that obviously you're going to get a lot smaller resistance. So on to testing. So insulation resistance testing is a fundamental test for inspectors. It's one of the tests that we have to do. These tests are to verify that the installation of the conductors provides adequate insulation. It is not damaged, and the live conductors or protective conductors are not short-circuited. So it really means that there isn't a fault somewhere, someone hasn't put a nail or a screw through the cable, someone hasn't trapped something in the lid of trunking when they put the lid on. These are all things that I have actually seen. Someone's forced some lid on a cable and it's trapped a live conductor. I've seen a screw go through a cable. So we're just checking to make sure. And obviously we do not want to liven up a circuit if there is a problem. So it's one of the fundamental tests we do. So the types of test instruments. An insulation resistance tester should be used, which is capable of providing a DC voltage as specified in the table 61 below. And I'll show you a copy of this table now. And this table also specifies the minimum permitted value of the insulation resistance. And we would normally expect to get a higher value, but it gives you the minimum. So what you've got here, so if we were using low voltage installations, and I've got a little handout and I'll show you about the low voltage now, we would use a test voltage of 250 volts. And the minimum insulation resistance we get is 0.5 megaohm. Now, in normal situations, we would expect to get, for our things, up to and including 500 volts, with the exception of the distance below. We would use 500 volts, and we would expect to get 1 megaohm as a minimum. And above 500 volts, we would use 1,000 volts at 1 megaohm minimum. So these are the type of things that, you know, so this is why we have the different testers and the different sizes that we would use. So pre-test checks. Before commencing the insulation resistance test, a number of checks should be made with precautions taken as follows. The protective conductor of an item, switchgear or cable, is connected to the main earthing terminal. So we need to make sure that the protective conductor is connected to the MET. Pilot or indicator lamps and capacitors are disconnected from the circuits to avoid inaccurate test values being obtained. If you think a pilot light or an indicator light would come across as a short, because it goes between live and neutral. And because it goes across live and neutral, if we were doing an insulation resistance test between live and neutral, it would appear to be a short. So we have to make sure anything with a pilot light, an indicator lamp, anything with a near lamp is removed from the circuit, because it will give you a false reading. Voltage sensitive electronic equipment such as dimmer switches, touch switches, delay timers, power controllers, electronic starters for fluorescent lamps, emergency lighting, and RCD and similar equipment are disconnected, so they are not subject to the test voltage. You know, it will give you a false reading, and also they do not like having the 500 volts put through them. You know, dimmer switches, the electronic components on a dimmer switch are rated to be, you know, that they will handle the 240 volts, 230 volts. They do not like 500 volts being applied through them. So insulation test on a whole insulation resistance testing on a whole insulation. So in this case, you can see you've got the whole circuit there, or we've got two circuits. And what we've done here, first of all, we've removed the lamps. So the lamps have been removed. As I said to you before, like a neon, a lamp, the filament of a lamp goes between line and neutral, and that would act as a short. It is a short. Obviously, when we apply a current through it, it's designed to light up, but it would be a short on the test. So we need to remove all the lamps. And as you can see here, we put the tester onto the neutral bar, and we put it onto the outgoing of the main switch. Yeah, so onto the buzz bar, and that tests the whole of the circuit. Obviously, this circuit only has two circuits, whole installation, and we would get a reading here. And obviously, if we got a decent reading while we were doing the whole installation, then we know that that's okay. When we do our testing for your exam, I would expect you to do every single circuit individually, just to prove that you can do that. And as I said to you before, when we're doing it in the college environment, we want to go back to the manual. We want to go back to doing it every step of the way, just so we do it. So on some of the circuits we have there, we have 3, 4, 5 or 6 circuits. We would do that 6 different times. But this is just showing you that you could do the whole installation. So on a single final circuit, and the only difference here is, once again, the lamps have been removed. We would test the neutral bar, and we would test the specific circuit. Now, what I didn't mention, or what I need to go through, is with the two-way light switches, or the light switch on, we need to do the test once with the light switch off and once with the switch on. So what we're doing is checking that we're checking all. So in this circuit here, we're checking all the way down to the switch and back up. We're checking the whole circuit. And it would be the same with the two-way lighting circuit. We would do the test once with this switch off, then we would do it again with this switch on, and then we would do the switch again. So we're checking all the strappers. If we weren't to do that, we would check this part of the installation, but we would not check this. So we need to make sure that we're doing that with the switches. So you check every time you flick the light switch on and you flick the light switch off, and you make sure that you're checking the complete part of the circuit. So when it comes to three-phase, so this is the testing for three-phase, and this looks very similar to if you were going to do safe isolation on a three-phase circuit. So you would do an insulation resistance of L1 to L2, L1 to L3, and L2 to L3. So you would check all the line conductors individually. You'd check all the line conductors to themselves individually. But then what you would do is you would check L1, L2, L3 connected together to neutral, and then you would do L1, L2, L3 together to earth. So you'd be checking them all to neutral and then all to earth. And then the last test is neutral to earth. And it is essential for test 5 and 6 that the earth is connected to the installation earthen terminal. So it's very similar to the safe isolation procedure, but you're just checking on the three-phase. So you've put L1 for test 4, L1, L2, L3 together to neutral, and while they're all together, then you test them to the earth. Obviously, with an armored cable, you would check the insulation resistance to the armored cable. Which is a little diagram there. Okay, I am going to just stop my little presentation, the recording, if I can get out.